Good afternoon. So let's start with a nice warm up today. So I just want a random triangle here. Ugh. We'll call that a triangle for lack of a better word. Let's say that is 70 degrees. Let's say that is 4 units. And which one do I want? How about this one? Let's say it's 5 units. Find all other values for any possible triangles. So find A, B, and side B. While you work on that, Jasmine and Nicholas, is there anything else that you wanted to look at today? That's better. Small crowd today. Good afternoon, Nick. So we're just looking at a little warm-up problem here, Nick. If there's something else that you want to look at or something else you had questions about, let me know. Post it up. If not, we'll just play with some different types of problems today. So Nicholas, Jasmine, or Nick, you want to suggest which tool we want to start with here? Nicholas wanted to go with law of sines. Anybody want to argue with that? Lots of agreement. Let's say somebody disagreed, just for sake of argument. Let's say somebody went, oh no, This is our angle side case. That's our angle side case. We don't like that case. And we can tell. These are the jokes. That angle side case is where we run that risk of the whole ambiguous solutions thing from using sine. So let's say somebody said, I don't want to do that. I want to use the law of cosines instead, because the law of cosines gives us unambiguous answers, supposedly. So it's the one big criticism that people often have of law of sines is the whole ambiguous case thing. And so let's say we felt that way and wanted to do that. So law of sines, we need an angle and a bunch of sides. Okay, we've got that. So if we tried to set it up with law of sines, well, we have an opposite pair here. Sorry, law of cosines. We have an opposite pair there. So we'd have to say that 5 squared is equal to the 4 squared plus that b squared minus 2 times 4 times b times the cosine of that 70 degrees. Remember that angle, the whole thing equals the square of the side opposite the angle in question. So that 70 has to go with that 5. So, okay, we could, we're students of algebra, so we certainly know how to handle something like this, but we'd get a little bit icky. Minus 8 times b times the cosine of 70 degrees. But remember, the cosine of 70 degrees is just some number. So that number times 8 would be the coefficient of b. But we have a b squared here and a b. If we tried to solve for that b, we would need to set this equal to 0. We wouldn't be able to factor it. So we'd have to use the quadratic formula. We'd get b equals, something plus or minus the square root of something divided by something else. That plus or minus would give us 2 answers. Even using a law of cosines. So the point of this, never do this, by the way. Never use law of cosines this way. It's just a useless pain. But what I want to illustrate is the fact that this ambiguous case, the fact that we get these 2 answers, isn't a flaw in the law of sines. It's a flaw in the information that we're given. The fact that this angle side set of information is by its nature ambiguous. The law of sines just shows us that ambiguity and allows us to find the possible answers based on that ambiguity. It's really not the law of sines' fault. Law of cosines would do the same thing, and in a much worse way. So keep that in mind. But yeah, never use law of cosines that way. It's horrible. It's just vile thing to try to do. I mean, it works, but putting it into the quadratic formula that way, just ugly. Get the profanity off my screen. Because we have that opposite pair, using the law of sines, yes, we'll get the ambiguity, but we'll get it much nicer, much cleaner than we do trying to use law of cosines. So the sine of that 70 degrees in ratio to the 5 is equal to the sine of the A in ratio to the 4. So that nice 4/5 sine 70 degrees is equal to the sine of that angle A. And when we use the inverse, we naturally get 2 answers. We just have to decide if both of them are valid. If any of them are valid, it's if one of them is valid. So I'm going to grab this nice little sine inverse of 4/5 times the sine of 70 degrees, and hopefully I've remembered that this calculator automatically puts itself in radian mode when I start it. So let me fix that. Okay. So that gave me what looks like 48.7 degrees. Now that's, of course, our principal answer. So that's the acute 48.7 degrees. There's also going to be another angle over here where that reference angle is still 48.7 degrees. So that's going to be what, 131.3 degrees. So, or 131.3 degrees. So those are our two possible angles from the sine inverse. The acute one will work. That would give us 70 degrees, 48.7 degrees, and we could subtract from 180 to find the other one. What would that be? That'd be 118.2, 0.7. From 180. So I keep wanting that to be a 2. Anyway, gotta do my subtractions by hand here. That'd be a 7, so a 9, so a 1, so a 6. Yeah, 0, so 61.3 degrees. Yeah, that looks right. And that's still our 4 and our 5. So that left us with a 61.3 degree angle, perfectly reasonable angle. So that's one triangle, and we still have to find that length B. The 131, when we try it, if this was 70 and that was 131.3, that's already 200 degrees. If we tried to take 180 minus that 201.3 degrees, we're going to get something that's some negative angle. Well, that's not possible. Okay, so there's no second triangle. So we get to ignore that second case, which is always nice. So then we just need this side length B. Now, we could use law of cosines to find that side length B if we wanted to. We could say that the B squared is equal to 4 squared plus 5 squared minus 2 times 4 times 5 times the cosine of the 61.3 degrees. We could certainly do that, but that's a bigger tool than necessary. Perfectly legitimate thing to do, but it's just, we're, using the big hammer on the medium-sized nail, where the law of sines is probably faster. And because we're finding a side length, we have no worries about ambiguity. I'm going to use the 5 and the 70 just so we use as much of that given information as possible. But we can then find that side length B pretty quickly using law of sines. I'd expect that to be what? This is the medium angle, so that side length will be somewhere between the 4 and 5. So 5 times the sine of 61.3 divided by the sine of 70 degrees, 4.54. 4.54. So that 4.54 is that other length. So a nice little review of a law of sines question. How do you guys feel about that? I know you guys are going to have to talk more than you usually do because there's nobody else around here. Nicholas, you're happy with that? Jasmine, Nick, what about you two? Might be catching up on those notes. No, yeah, no, or yeah. No, yeah, doing good. Okay. Nick, if there's a question in there somewhere, let me know. But let's look at some practical applications. Even nowadays, in the realm of laser rangefinders and so forth, we still end up using some of these tools in everyday applications. Well, depending on what you're doing every day, I suppose. So let's say you're here at some location and you're, I don't know, trying to figure out the distance between this tower and this tower. You want to find out how far apart they are. Well, even with our modern tools, our laser range finders and stuff will tell us how far away this is. So say that's 4.2 kilometers. And our little laser range finder can tell us that that is, say 5.1 kilometers away. If you have even just a protractor that you can put sights on, or again, your phones have angelometers and stuff in them. So we could determine that this angle is, say, 34 degrees. We can use that information to find the distance between these two objects. And again, this works for things like, towers or trees or mountains or that kind of stuff. It also works nicely for celestial bodies and that sort of thing. We can use some of the tools we talked about before for finding how far away different stars are, but then we want to find out how far away those stars are from each other. This is a very nice tool. So, gonna let you guys do that again. Take a moment, determine how far apart those towers are. No trouble. So which law do you want to use here? Law of sines, law of cosines? How do we tell? Nicholas, I'm going to be a little bit argumentative. We don't have enough information for law of sines. We don't have the right information for law of sines. We still have three pieces of information. We just don't have one of those opposite pairs. You're right, though. If we did have more information, that other side, we could use law of sines. Um, but you know how picky I get with how we say things. But yeah, we don't have that opposite pair that we would want for law of sines, and law of cosines builds that. That's its job, or one of its jobs. So law of cosines, it'll be. And then we can, again, label this side, anything we want, call it A. And this is a fairly nice, really straightforward, I guess, direct use of our law of cosines. Biggest danger is then making sure we, one, type all that in correctly, and two, make sure we remember to square root the result. So that squared plus that squared minus 2 times the 4.2 times the 5.1 times the cosine of 34 degrees. That gives us, what, 8 something? Now, that 34 is a pretty small angle, so there's no way that side length is 8 something. That would make that 34 the largest angle. There's no way. Well, that's because we didn't square root, or I didn't yet. 2.85, that sounds better. 2.85 kilometers apart. This is 8-ish. Took the square root. And technically we get plus or minus 2.85 and so on. But we certainly take the positive one. So as I mentioned yesterday, people usually like these tools, law of sines and law of cosines. They're very visual. There's not a lot of that kind of trickiness that goes on in chapter 7. So people tend to be pretty happy with 8182. We could have a little bit more fun with it. Let's say we've got some nice triangle here. And let's say we know this corner. It's actually a pretty common set of information to have, because from this one observation point, we can find an angle, and we could find those two lengths with things like range finders or whatnot. So I'm going to call that 7 and 12. And yeah, we could use law of cosines to find this other information there, but I want to find the area of that triangle. All of a sudden. Now, certainly, you guys remember the formula for the area of a triangle. Formula for the area of a triangle, good old 1/2 base times height. It's actually kind of an unfortunate formula, mostly because it's really not as common as we might think or be led to believe in our mathematical background to know that height. If we've got a triangle here, measuring angles, well, you need a protractor. Measuring side lengths, you need a ruler, tape measure, laser rangefinder, whatever. But accurately measuring that altitude. Accurately measuring this height is tough in practical application because that needs to be a perfect right angle. So it's often quite difficult to get that base and height in practical applications. The nice thing is, when we built our law of sines, you might remember, we found that h in terms of the 40 and the 7. We found that the sine of that 40 degrees had to be equal to h over 7. So that h height turned into 7 sine 40 degrees. And we did that for the other angle and built law of sines out of it. But it actually gives us a very nice tool for finding height and thus finding area here. The idea that the area of this triangle is then 1/2 times, okay, we're still going to be multiplying it by that 12, the base, but we're also going to be multiplying by this other side and the angle between them. So we often simplify this formula to AB sine C, where that B sine C is that height, or the A sine C is the height if you prefer. They're just labels, so we can label them anything we want. As long as those are two side lengths and the angle between them, this is often a much more useful formula for area of triangles once we're comfortable with using trig. I remember in one of the calculus classes I gave, we came up with a problem that we were trying to solve with areas of triangles. And I think all but 2 people in the class were trying to use this formula for the area of a triangle, which worked, but it made the problem very long and very, very cumbersome. A couple folks grabbed the same problem and used this formula. I think it was only 2 of them used that formula for the area of a triangle, and it was a really quick problem. It took 2 or 3 minutes and it was done, as opposed to the other one, which took I think about half an hour. So it's a surprisingly handy formula once we're comfortable with our trig. You ask a lot of people who do a lot of geometry or calculus or differential geometry, what's the formula for the area of a triangle? They'll often tell you 1/2 AB sine C, as opposed to the 1/2 base times height, just because it's that much more convenient. So we want to find the area of this triangle. All right, area of the triangle. 1/2 times 7 times 12 times the sine of that angle between them. And that'll give us a super accurate little area. 1/2 times 7 times 12 times the sine of the 40 degrees. What's so 26 point 2700. So I'm going to say 27 square units. So that's kind of a nice tool that comes out of this argument for area. Or sorry, our tool that comes out of our argument for law of sines and law of cosines. They both used that, turning that height into a sine argument. One of the nice outcomes of that is we have a nice tool for finding heights for things like areas. Your textbook talks a little bit about Heron's formula. It's a really old Greek formula. It's named after actually Haran in the Greek pronunciation, but we nowadays call it Heron's formula. That's a formula for the area of a triangle if we're given 3 of the side lengths. So if that's, say, side length 7, side length 5, and side length, 10, it's a formula for finding the area of a triangle given just side lengths, because oftentimes that's what we can measure nicely. but it's a very cumbersome formula. You can see it in your textbook. It's the, oh, if I can remember it, it's the square root of what, s and a minus s, or s minus a, I think it's s minus a, s minus b and s minus c, where s is equal to this formula with a, b, and c. It's just this cumbersome little formula. But if we can use law of cosines to find this angle, the fact that 7 squared has to equal 100 squared plus 5 squared, almost put 25, minus 5 times 10 times the cosine of that angle. If we can find that angle, then we can use this to find the area in a much faster, much nicer way. Why did I put 100? Oh, because I squared it and then squared it again. That was silly. Did you guys yell at me? No, you didn't. Guys are not watching out for me. Oh, I forgot my 2 as well. I got so excited. 2 times 5 times 10 equals the cosine of A. And because it's cosine, it'll be the principal inverse. So we can, without loss of any information, just use the straight cosine inverse in the writing. And that's going to be our angle A. And then use that nice little formula for the area. Now, it's certainly using a lot more tools, a lot more sophistication than the ancient Greeks had, but it's a lot nicer of a couple of tools than that big Heron's formula. So the area would then be 1/2 times the angle, or the sides that make up the angles, times the sine of the angle between them, which, unless somebody has a decimal approximation for this right now, we could just use the cosine inverse of 100 plus 25 minus 49 over, what, 100? And that would even be a nice exact value. And heck, even the sine of the cosine inverse, we've done those symbolically. So it does generate a nice tool for us for area. You guys are being awfully quiet. Any questions about that? Is there any particular type of example you guys want to look at or play with? You guys happy with these tools? Let me see if I can throw you off. Do we just want to talk about our feelings? Are you guys happy and just want to go about your day? Nicholas is happy. Well, I don't want to just throw you guys out. Let's look at one other type of example. We have an example here where we had the angle side side. That's always the kind of messy case. We had a one here that was side angle side. That's always a nice case. This was side angle side. Here we had side side side, and we did a couple examples like this yesterday. We wanted to make sure, to find that big angle last or first. So if we wanted to find these angles, we talked yesterday about which one of those we'd want to find first or last. I wouldn't want to find this one with law of sines. So I would find this angle and then that one to avoid the issue with the ambiguity. But we haven't looked at a particular type of case that's also kind of interesting. So let's say we have a triangle that we need to build or find or whatnot. And we want this angle to be, say, 70 degrees. We want this angle to be 60 degrees. That means this angle will have to be, 50 degrees. So those are the angles our triangle needs. And somebody asks us to find the side lengths. What are we going to do? How do we find those side lengths? I'll let you think about that. Decide how you'd want to proceed. If you have any thoughts, let me know. Or concerns, or hey, wait a minute, or Jasmine or Nick, what about you two? Thoughts of either how you'd proceed, or thoughts about why proceeding is troublesome, or general questions? What do you got? nice hearty, I'm not sure. That works too. Not sure how you proceed with just having angles. It is weird to just have angles. The main issue with just having angles is that this triangle could technically be any scale. This could be a little tiny triangle this big, or it could be a gigantic triangle that's somebody worked into a field of crops that you can only see from an airplane. We have no idea how big this thing is. So how are we supposed to get side lengths? All of our tools, law of cosines needs at least 2 side lengths. Law of sines needs at least 1 side length. And we know that the side lengths could kind of be anything, but they can't be really anything. For example, if this side length was 12, as soon as we picked the 12, the other 2 would lock in. So they can't be random values. Those 3 side lengths do exist in a ratio. They have to have a particular ratio to them. So what we tend to do when all we have is angles, we don't try to give specific side lengths. We give a set of proportions. So we generally pick one side length, it really doesn't matter which one, and call that side length arbitrarily length 1. You might remember we did this with the 30-60 and the 45-45 triangle weeks ago. We wanted to find the ratios of sides, so we just arbitrarily picked one of the side lengths to be 1. Doing the same thing here. Now, in doing those, I chose the side length 1 to be the hypotenuse for a convenient reason when we got to the unit circle. Here, I am purposefully choosing the side opposite the largest angle, but you don't have to. It could technically be anything. It will make these 2 sides be numbers less than 1 and essentially gives us proportions. Like say this was 1, and I'm going to make these numbers up. Say this was 0.82 and this was 0.91. That would mean that whatever we make this length opposite the 70, this length will be 82% of that. This length will be 91% of that. So it still allows us to figure out what the side lengths would be, but as a general proportion. So using that 1, we do have an opposite pair. So we technically don't even need law of cosines here. If we wanted to find, say, this side length, we know that side length in ratio to the sine of the 50 degrees has to be equal to 1 in ratio to the sine 70 degrees. So A would just be that ratio between the sine 50 degrees and the sine 70 degrees, whatever that ratio is. So what, sine 50 divided by sine 70, 0.81, 0.8. It's actually pretty close to what I said, wasn't it? 0.82 if we round. So whatever this side length is, this side length will be 82% of that. So, if this was 12 feet, then this side length would be 82% of that 12 feet. If this was 194 centimeters, this side would be 82% of that 100 and whatever I said, centimeters. To then find the other side, same basic tool. So that B in ratio to the sine 60 degrees is going to equal that same 1 over the sine 70 degrees. And B will be that ratio between the sine of 60 degrees and the sine of 70 degrees. So I'm just going to take that, change it to a 60. Those are awfully close to what I said. I didn't mean to do that. 0.92. Is it 92? Lost it on my thing. Yeah, 0.92. Okay. So again, whatever side length we then, somebody assigns to the side opposite the 70, that's 82% of it, that's 92% of it. So when we have our side lengths are 1.82 and 0.92. We just, those are in scale to each other as opposed to being specific set values. Jasmine, does that make sense? And that's why I want you guys to see it, because it is kind of a weird question. It's like, well, we don't know, but we also know they aren't just 3 arbitrary values. So, but yeah, because we don't know the scale, we just essentially put in that 1 as a scaling factor. Why does C equal 1? Because, unfortunately, Nick, the short answer is because we said so. We could have picked any of them to be 1. So let's say we wanted to do that. Let's say instead we wanted to be able to choose this side. If we wanted to be able to pick the value for this side and find the others, we could let this side be 1 and then figure out what these other 2 are in proportion to that. Now, this is going to be a number greater than 1 because it's got to be larger than this side. That would be less than 1. And we could find that set too. So we'd be doing the same thing. 1 in ratio to the sine of 60 degrees is equal to, I'm going to call that B, in ratio to the sine of 50 degrees. And then for the other one, the sine of 60 degrees would be the C in ratio to the sine of 70 degrees. And we're going to get different values than those. Let's find them. Excuse me. That would make B that sine 50 divided by sine 60. So sine 50 divided by sine 60. That's 0.85. So that B would be 0.85. And then the one opposite the 70, oops, that's not what I want. That's what I want. So sine 70, wait, that's not right. Yeah, I don't trust that. You guys are finding these too, right? Let me redo that. Sine of 50 degrees divided by sine 60 degrees. Yeah, that's better, 0.88. I had misplaced a parenthesis. And then the sine 70 divided by sine 60. And change that to 70. So 1.09 roughly. So okay, so that has changed our answer to 1.88, 1.09. That might seem like, well, those aren't the same set of information, but they do make the same triangle. It's just we're choosing a different side length. So here, if I want to make this value, say 12, then what are those two values going to be? Well, 82% of 12 and 92% of 12. So 0.82 times 12, 9.84, 9.84, and 92% of 12, 0.92 of 12, 11.04. So those are our three side lengths, and we know where they go because the smallest one has to be opposite the 50. So the one opposite the 50 has to be the 9.84. The one opposite the 70 has to be the long 1. The one opposite the 60 has to be the one in the middle, the 11.04. Now I'm saying that's the same as these values. Well, if we grabbed that 11.04, that's supposed to be our value for this side. So if we let this be 11.04, hopefully, if this is correct, 88% of 11.04, that should match the 9.84 up to approximation. The 1.09, 109% of the 11.4 should equal 12 up to our decimal approximation. So it should yield the same set of values, just with a different orientation. And I'm actually really curious to make sure that works. So 0.88 times, I mean, theoretically it should work, times the 11.04 is, let's see, 9.7. So it's close. We did some rounding in there. And the 11.04 times 1.09 is hopefully fairly close to 12, 12.03. Okay, great. So yeah, we could carry more decimals if we want it to be nice and accurate, but these three lengths defined that way, and these three lengths are the same lengths. They're just ratios in different orientation. So we can essentially choose any side length we want to be a 1, and then figure out everything else in ratio. Again, by habit, I like to choose the biggest one to be 1. That way everything else is a less than 1 percentage, but it really doesn't matter. Nick, does that work? Cool. All right. So go play with the law of sines, law of cosines. Tomorrow we'll start looking at vectors. And if any questions come up between now and then, let me know. And I hope to see all of you tomorrow. And Garrett, if you want to see the first part of this, as soon as it's done loading, I'll try to put it on My Open Math so you can watch the first part. But we were just practicing with law of sines and law of cosines. Okay. Have good days. Well, I'm glad it's made sense so far. It's awesome.